Hello everyone, this is Dilleswara from Aeronautical department. So as we are discussing a few classes on automatic control of aircraft, so last few classes if you see my previous videos we have been discussing on displacement autopilot system and its control system integration and that solution of longitudinal equation of motion Laplace transform solution also been discussing from last few classes. But I think you have some doubts on what is this transfer function, how we got the transfer function by using this Laplace transform, and how these differential equations have been converted into transfer function. What are the theory behind that one? I think you will have some doubts on that one. So today in this class we will discuss on that solution method for finding out the control response by using Laplace transform method. So for any equation like whatever the transfer function equation if you see in any integrator, so that integrator equation will be generally in terms of Laplace operator yes only. So how that Laplace transform function has been came, so that only we'll see now with one small example also we will discuss. So that we already discussed in last classes, last few classes. If you see my previous videos, you can find that one. So let's go into the topic. So here, the Laplace transform. I mean, we have been using this Laplace transform from our. I mean, like if you are doing your engineering mathematics in your first year or first semester or second semester. So on that differentiation calculation equation, higher order differential equations. There, if you want to solve the equation with respect to that frequency modes and frequency response, you will generally use this Laplace transform function only. So I won't go deep onto this one, like because Laplace transform solutions and how this Laplace transform equation of will find how this integration equation is being converted to Laplace transform. That maybe you already know, and that is a pure mathematics thing. So you will have an idea on that one. So here I'm discussing on how the transfer function of an integrator have been coming out from this is a differential equation. So that I want to discuss here. So see here for the Laplace transform function, generally we will represent with L. So L of t. So we have some equations like L of e power at and L of sin at and L of cos at. So for this, the Laplace transform functions we already, I think you have seen. So L of at will be like what 1 by s minus a, and this will be like a square, a square by s square plus a square, and here it will be a square plus this. I mean this already these formulations you already may know on your mathematics background. So here, like that, for some equation, if you consider like y of s is a some function, and the function has been changing with respect to that Laplace operator s. So if it is been if it is been integrating with 0 to infinity limits. So like the equation we can take it as y of t into e power minus st dt. So that this y of st we have written like y of t into e power minus st. So generally that Laplace transform functions we will make it in time response to operator response. So there will be some each component will have a different values like L of x of x1 of t, x2 of t, or till if it is continuing till xn of t. So that I mean if it is in a time response function, this will be converted into Laplace operator function. So that operator function will be in terms of s only. So that s values only we will make it like a one algebraic form will be there. So that algebraic form will be making suppose again a fraction of method of fractions, that method we will use, and again we will make it into an algebraic equation only. So like that. So see here some equation, like x dot will be equal to ax plus b eta. So suppose one linear function we have considered like this. So x dot will be equal to ax plus b eta. Like in terms of x and eta, we have taken one function. So suppose for this, if it is been converted into Laplace equation, so how it will be? So that is for x will be like this x dot will be converted into minus x no x dot x of 0. That means that 0 value plus that differential form is converted into Laplace, that will be x of s, plus the here it will be like ax of s and b eta of s. So that means in terms of Laplace operator, we got one equation. So this is we are applying that. That means L of x dot if you do, then we will get this equation. So after that, so now we will make it as a variation and separation method. So if it is like what, so this a terms will be one side and b terms will be one side. So then what it will be, x of s will be equal to x of 0 plus I mean this will be go here, uh, and s into x of s plus a into this will be x of s into b into eta of s. So here if you x of s, if you take it common, so s minus a, right? So s minus a. So s is a general function only. So yeah, if you want to write it in a matrix form, so like in terms of unit matrix, how it will be, s into I will be we can write it as a unit in terms of matrix, and a also if you take it as a matrix. So this is all been converted into vectorial matrix form. So that will be si minus a means what, s 0 s minus a into x of s will be equal to x of 0 plus beta eta of s. So this will be the equation. I mean, we are making it into matrix form. So then we need the expression for x of s. So if you want to make it for x of s expression, so then what it will be, if it is this matrix, if it is go this side, then that will be the inverse matrix. So si minus a inverse into x of s plus beta n of s. So these are all constant form only. So then the matrix si minus si minus a inverse is called as a resolvent, and that inverse Laplace transform is called as a transition matrix. Like this inverse transform, this is a direct form only. If you give inverse Laplace transform to that one, will be call it as a transition matrix. So that transition matrix, if you write it like if you denote it with a phi of t function, so phi of t will be L inverse of si minus a inverse. So that will be equal to what? So if you apply that inverse matrix, so if you substitute that inverse matrix into above equation, so that will be L inverse of x of s will be equal to x of t. So that will be equal to L inverse of s of si minus a inverse into x dot plus L inverse of si minus a into b eta n of s. That means here, I mean for this only we are just for this only we are just substituting this L inverse of si minus a into here. Okay. So here we are substituting in terms of here, and we are making this into multiply with x of s into beta n of s. Okay. So then that whole equation will be like that. So then the convolution theorem can be used to write the inverse Laplace transform. So the convolution theorem is what? So if you are using this L inverse of inverse Laplace transform into this one, so that again it will be converted into matrix form with with variable function. So that will be like what? So if you are applying that integration to that one, so what it will be, so that this whole function will be x of t will be equal to phi of t into x naught plus the remaining function phi of t minus tau. So t minus tau means this is like a another variable. So here actually time variable t is there. So with addition to that tau also we have considered. So the total total function with in terms of t will be like what? Phi of t into x of 0 plus integral 0 to t phi into t minus tau into beta b eta of t into d tau. So this is like what the matrix phi, the transition state of a vector will have an initial value at x of 0 and its state later time at time t that including the effect of control input through convolution integration. So that will be the second term on this right side. So that means what? For initially the value will be getting out from x of 0 value. After some time t, the value we can get it with the integrator operator with this one. So if you see that integrator being included here, so like first the summer will be there. So after summer that amplifier will be there. After amplifier the integrator function like s plus 0.75 by s square plus 9 plus 0.8 something integrator function generally will be there. After this integration that input will be there. From that input one that rate gyro function also we will generally include here. So why this, I mean how this integrator function has came from this Laplace transform, that only we are just giving now. So next thing will be like matrix exponential matrix form if you want to make it. So like the transition matrix for linear time variant system, that is those system can be described in system differential equation in the form of above equation. So in which a and b, so like here you see that a and b that are constants only. So which are the matrices only. So the independent of time can be written in terms of so-called matrix exponential. So if you see here, so that for x dot equal to x, then the Laplace transform of above will be like we can write it like x of minus x of 0 plus x of s into x of s plus a into x of s. So the here that Laplace transform of x of s will be like what? 1 by s 1 by s minus a into x of 0. So this we can write that the inverse Laplace of this will be again will come into e power at. Like this is for direct Laplace transform. Then inverse Laplace transform of 1 by SA will be equal to e power at. So then the total x of t will we can write it like e power at into x of 0. Then phi t will be equal to e power at. Okay. So this is for a function in terms of exponential form. So if you write that 1 by s minus a expansion, like 1 by s minus a expansion, if you write it in terms of terms, so that will be like what? 1 by s into 1 minus a by s. So that will be equal to 1 by s plus a by s square plus a square by s cube plus a cube by s power 4. Like that it will go on. Like 1 by s minus a term. So that will be like what? So this we can write it in terms of common term. So that is like what t power n. So if t power n, if anything power t power n, Laplace transform of t power n will be equal to n factorial by s power n plus 1. So for above equation, so the thing will be like this one. That Laplace transform of t power n will we can write it like that. If the inverse Laplace of this one will be like n factorial by n plus 1 will be same t power n only, right? So same as for a 1 by s minus a. For a 1 by s minus a, if you write the inverse Laplace transform for that one, so that will be like what? 1 plus at square, like everywhere the t will be included. So like because the t power n is included here now. So like t power 80 square, 80 cube, 80 power 4, like that if it is goes on, then that I mean this 1 by s minus a inverse we can now we already wrote it before like e power at only. So that e power at again we can write that s minus a inverse like matrix inverse form also we can write like we can be equated into e power at. So then that matrix exponential can be write it like, so I mean this can be write it like I plus at square by 2 factorial at cube by 1. We here a means this is a matrix form only. That means in terms matrix that whole matrix inverse Laplace transform we are writing like this. Okay, so that conjecture verification if you want to do, so then si minus a inverse will be like what? I mean if you want to write this as a like this one, so that will be like what? I means identical matrix I by s minus a by s square plus a square by s cube by a cube by s power 4 like that. That means same as this one. You can write this si minus a inverse. We can write it like that. Then that equation can be verified by pre-multiplying si minus a to the above equation, so that I will be equal to I minus a by s. I mean if you make it like this, so a by s minus a by s square plus a by a square by s square minus a cube by s cube like that, it will goes on. So that successive term like I, if you make it as a 1, I mean I equal to 1. So then that inverse Laplace transform of Si minus A, we can write it like I plus At plus At square. I mean in terms of expansion, we can write it like that. So this will be anyway equal to e power At. So then that e power At again that e power At by using convolution theorem, that e power At we can write it like this one, that x of t will be equal to e power 8 into x of 0 plus integral of 0 to t e power a into t minus t and beta b into eta of t into dt. So that will be like what? If e power at if you take it out common, so that e power at into x of 0 plus integral of 0 to t e power minus at b into in eta of t into d tau. So like that means that exponential form we are making it make it into that general expansion. That general expansion is again write it into that by using time variant system, like a time variant function. If you want to write by using a convolution theorem, you can write like that. That means that exponential function also you can write like this. Okay, so next for this function only, what is the time response? I mean different response. I mean why we are using this integrator and transfer function here? Because this need to be used for. I mean this need to be used for making it as a frequency response diagrams only. Like we need to, if you want to draw a frequency response diagrams, we need to use that one. So like for different responses like system time response and impulse response and frequency response, how this equations will be behave. Like see, suppose one equation is forming like that. This linear equation we have written like x dot will be equal to ax plus b eta, and y will be we can write it like cx plus d eta. Like suppose if you assume a functions like that, then for this, the time marching functions we have already wrote with convolution theorem like what? So in terms of exponential, we have wrote like e power x into x of t. Then y of t will be like what? I mean here that a will be there, and here that c into e power a t into x of 0. So that means here that system response to this is the system response for several control inputs. Like if you give one a control input control input of x of 0, that means this x of 0 is the input function only. If initially function is 0, then it will be 0. If it is initially that from initial to time t, if you are giving input some more input, then this function also will be gives the frequency response of that control system. So that will be varies in terms of time only. Okay, like impulse response also, like for the same thing only, that impulse response you can write, you can take that eta of t. So eta of t you can write like a equation like eta naught into delta of t. So here that eta naught we can write like in terms of delta, like delta 1, delta 2 naught, delta 3, like delta p naught transpose, like that means these are all deflections. I mean, if you see in deflections of inputs, like that values we can write it in a matrix form. So this will be like generally ax equal to b. So a into x variable we can write like x1, x2, x3, like that. So these are all variables only. So these variables we can write it like in column matrix. So if you write a transpose to this one, so that will be the transpose of this one. Like a transpose to this will be this matrix. Okay. So if that is the case, then by using that integrator for this function, so that the integration may be like minus infinity to plus infinity. So delta of t minus tau into dt will be equal to 1 only. Okay. So that integrator 0 to t e power minus 18 into b eta naught into delta of t d tau will be equal to b eta naught. So then that x of t and y of t we can write it like e power at b eta naught and c into e power at. So like previously how we can write that frequency response, like that only we can write like why we are telling that this one function, if you write it in frequency response type, so you can use this equation. So from this you can easily write that one. So like see that beta that vector b eta naught can be represented interpreted as a specified initial perturbation, like suppose one control input perturbation input, if you are giving like x of x naught, then we can see that the system's response to an impulsive input t equal to 0 is equivalent to the homogeneous solution for specified x of 0 will be equal to b eta naught. So like for a particular input, if it is that the control input is starting from 0 to some value, so that value if that value is changing, then that frequency response also we can get it by using this equation. So next will be that doublet response. So doublet response means like same impulse response only. How that doublet response will be like. So suppose if you take that eta of t in terms of eta naught into d delta t by d tau. So for this, if you apply the same time marching solution, so that is also we can write like x of t will be equal to e power 18 into AB eta naught, and y of t will be equal to c a e power 18 into ab into eta naught. Like this equation again we are writing in time marching solution like this only, like previously we have wrote now by using that. I mean these are all different types of response methods. By using these methods only we will solve that frequency response equation into these methods. Okay. So next step response. So step response will be like same equation only, that eta of tau will be that eta naught into h of t. Like if it is a h that heavy side step function, like if you write it like a heavy side step function h of tau, so that h of tau we can write like 0 1. So that 0 t e power 18 into b eta naught h of t will be equal to integral 0 t e power 80 e power 80 into e power 80 into b eta naught d tau will be equal to 0 to t e power minus 80 d tau into b into eta naught. Like h of t, if you write it in exponential form, you can write like that. So that we can write like that 0 to t e power minus 80 d tau will be equal to, so 0 to t I minus 8 tau plus a tau square. Like again, if you this is in terms of e power minus at. So that e power minus at, if you want to write it in exponential form, I mean expansion form. So like previously we wrote now that I minus a tau plus a tau square by 2 factorial minus a tau cube by 3 factorial, like that. So again, if you are making it into that matrix form, so that matrix form will be like I minus e power minus at into a inverse, like that. I mean, if you write it in terms of matrix form, we can write like that. So then the frequency response for this type of matrix, heavy side matrix, if you write, then that x of t will be right like x of t will be equal to e power at minus I into a inverse into b eta naught, and y of t will be equal to c into e power at minus I into a inverse b eta naught plus d eta naught. So for a stable system, so generally for a stable system, that t will be t will be going to the limit up to infinity limit. So if that limit t infinity, t tends to infinity, e power at we can write it like a 0 only. Then if it, x of t, for a function x of t, for this function that limit t tends to infinity, x of t will be like what, a inverse beta naught. So because the e power at will be 0, then I will be 1 only. So that will be minus of a power inverse into b eta naught. So by this, what we are concluding, like by using this type of different functions, like how this Laplace transform function is being used for writing the frequency response by using different types of inputs, like for a step impulse, step input, impulse response, step response, impulse response, and doublet response. So this type of response diagrams, why we are using, like if you need to give an control surface input to control surface input through an integrator. So how that integrator frequency response will be behavior, like how that behavior of that control surface will be there. So for that only we are explaining all these things. So you can see with this one example. So this Boeing 747 example we have already discussed in solution of equations of motion of an aircraft. At that time we have given this example only. So there, that Boeing 747 is powered at Mach 0.25 at sea level condition. All the values have been given only. So for this, the frequency response, how we can write. So for that, different values like velocity is at 279 feet per second. That the density of air at that condition is 0.0023777 feet cube, and span area S is 5,500 feet square, and the chord length is 27.3 feet, and weight of that aircraft is around 5,64,032 pounds, and IY of that whole aircraft is 32.3 into 10 power 6 feet square, and that stability derivative values, that coefficient values also, this is all we can get it from the data sheet of that aircraft only, like CL, CD, theta naught, CL alpha, CL alpha dot, CLQ, CLM, CL delta E, CD dot, CD alpha, CM alpha, and CMQ. These are all values we can get it. I mean, while you are designing that aircraft only, you will get these values. And this XU, XW, ZU, ZW, ZW naught, ZQ, Z delta E, MU, MW, MW dot, MU, MQ, and M delta E. So for these are all stability derivatives only. So that stability derivatives already we have a relation with in terms of CL and CD alpha. Like XU, you can write it like a DCL by D alpha. So from there, that XU value you can get like that, XW and ZU value also. If you see that the previous stability derivative one content we have given, no? Like one list of values we have given. On that list of values, you can find the formulas for each and every variable for this one. So if we got the values of like this, so then we have a matrix A. That matrix A, how we got these XU values only. See here. So first value is 0.02212 and 0.0466 and 0 and 0 1 minus 1.153. So these values where we got it, we got it from this xu xw value only. Like how we wrote this one. This value is in terms of differential function only. The differential function we have applied the Laplace function for this one. Then that equation, big equation we will get. That big equation is that coefficient of that equation. We write it like A matrix, and that equal to terms we write it like a B matrix. So here the variables we need to find out is what? U by U naught, alpha, Q, and theta dot. So for this only, that frequency response values we will write. So U by U naught, alpha, Q, theta, how these values generally we will write. So that here you see, for this solution of this matrix, we have explained two types of approximation for this one: the short period approximation and cuboid approximation. So by solving this equation, we will get equation in terms of Laplace transform, maybe like s power 4 plus s cube plus s square plus s plus constant equal to 0. Sometimes a big equation we will get. From this equation again we will get the roots of this equation. So that roots we will that roots we will write that short period approximation zeta and cuboid approximation omega np. So this omega np and zeta values also we will write. So from that, how that short period approximation and cuboid approximation with respect to time we will see. You just see the response of frequency response for this one. So first one you see the response of Boeing 747 for at a sea level condition at impulsive elevator input. That left plot, this one, the left plot is for the short period response, and right plot is for cuboid response. Like short period and Fugate response. Like see here, that speed u and the angle of attack, pitch rate, and pitch angle. That means what? What are the values we have given here? So speed will be u by u naught, angle of attack, pitch rate and pitch angle. So that values for the different values we wrote we have wrote this frequency response thing. So this frequency response thing you can write it from that oscilloscope method also you can write, or maybe by using MATLAB you can write this equation like MATLAB Simulink. If you give that function, like that function is there here now. So if you give this function, like if you solve the above matrix, we got the values for u by u naught, alpha, theta naught, and q. We got this value. So for different times, like 0 to 20 seconds, for that for that period of time, how that frequency response of each values have been changing. So that frequency response, that trend of that curves only we have wrote like that. So these are all MATLAB generated curves only. So you can try this one by writing a MATLAB code for the above equation and above matrix. If you solve by using MATLAB Simulink integrator module, so that you can get this MATLAB this frequency response easily. So like here also for for the other level, like this is also at a sea level condition only. So this is for 1 degree step elevator input. So this is previously is what impulsive elevator inputs. So this is for 1 degree step elevator input. Like here we are giving that. If you remember, previously we discussed about pitch orientation control and displacement autopilot time. So we have given that elevator input in terms of degrees only. Like this much of, in terms of degrees means what? This much of signal we are giving. For that signal, how much degrees of that elevator is been moving. So that elevator movement we have discussed in terms of per degree only. Volt per degree, like for this much of volt signal, this much of degrees that elevator is being moved. Also, after pitch orientation, acceleration control system also we have given. On that acceleration control system, how we have given? for giving this much angle of that lever. So this much of acceleration we got it. So per g, like volt per g, sorry, degree per g terms of values we got. Like degree per g means what? This much of voltage we are giving. So for that voltage, for that degree, like suppose this is a control stick. We have given some 1 degree movement to this one. For this 1 degree movement, that analog thing will be converted into digital say voltage signal. That voltage signal will be like if you remember that block diagram. So one summer will be there. So after that amplifier, that eg will be there. So after that amplifier will be there. After amplifier, one that integrator function will be there. After that integration, aircraft control system, dynamic control system will be there. Then it will be go to that that the output will go give you as input to that control surface. So here again one rate gyro feedback system will be given in between this one. So here in summer, here we will include one summer for this one. So again, another feedback will be given to this entire feedback. Like entire feedback also we have entered into that. So this is the block diagram we have used for that pitch orientation and acceleration orientation. For acceleration, here one accelerometer will be there. That accelerometer will give you the feedback for that summer. So this block diagram itself is giving like this much of control input is required for giving that control system deflection. So like that, if we are giving that control surface deflection, how that that input will have a frequency response. Frequency response means in terms of signal only it will need to go, no? So for that, say, if you are giving that type of input, how that signal frequency will be there. So that only we are giving in terms of two types of approximations. So that is short period approximation and phugoid approximation. So in this, which is used for which one, that also we have explained previously, like a short period approximation for a type 1 system and phugoid approximation for fighter jets and all. And for type 2 system also, if you include that rate gyro feedback to that one, then that signal will be furthermore accurately will give to that control system, so that the control system will be accurately it will operate. So like that, these are all things we have already discussed previously. So this is all about that autopilot system. So that's all about this equation. I hope you understand about you got some like overview on Laplace transform, how this Laplace transform is used for making a transfer function also. You may have an idea with this one. So that is all about this one. So this is the books we have I'm following for making this videos. So you can refer that books for further reference. Okay, so that's all about this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.